chapter 9 will concern the linear functions, also known as homomorphisms, between vector spaces. In this first lecture, we will give the definition and then the basic properties of these particular functions. Let's say a few words about why we need these particular kind of functions. And the most immediate way of comparing two objects v and w in mathematics is to try to find an application from v, or a function from v to w with certain properties. If v and w are vector spaces, they are sets in particular. So we can consider set theoretic applications from v to w. It turns out that they are almost useless to study vector spaces. For instance, we can always find a bijection between Rn and Rm for any n and m greater or equal than 1. Hence, for set theoretic applications, all Euclidean vector spaces are the same, virtually the same, meaning by the same when we can find a bijection between the two sets. We have seen in the previous lectures that as the vector spaces Rn and Rm are radically different. For example, Rn has dimension n and Rm has dimension m, and if n and m are different, they cannot be considered to be equal or even the same. They even have a basis with different number of elements, so they are totally and radically different objects. The reason of the uselessness of set theoretic applications in studying vector spaces is that they do not necessarily preserve algebraic structures which make the sets v and w into vector spaces. In particular, any bijection that we mentioned before between Rn and Rm will not certainly respect the algebraic structure of Rn, nor those of Rm. In particular, it will not respect the operation sum and the multiplication by scalar. What does it mean will not respect? Well, we will make this more clear in what follows. The remedy for this is to only use a special kind of set theoretic applications between vector spaces, if you want to study them. Definition: let v and w be vector spaces. A set theoretic application f from v to w is linear if the following two properties hold. The first one being that if we apply f to the sum of two vectors in the domain, so let's suppose that v1 and v2 are two elements in the domain, we apply f to it, then this is the same as applying f to the first element and then applying f to the second element and summing the images. This is called the linearity of f with respect of the sum. This is what means respecting the summation algebraic structure of v and summation algebraic structure of w. Notice that the first sum on the left hand side is taken in v, and the sum in the right hand side is the summation defined in w. By this we mean respecting the summation structure of both vector spaces. Likewise, the property b gives a linearity of f with respect of the multiplication by scalar. Notice that we cannot really mimic the definition of before, that would be f applied to lambda v equals to f of lambda times f of v, because f does not act on lambda. Lambda is a scalar. These two vector spaces are assumed to be vector spaces over R, like all the vector spaces in this course. But V does not act on R. R is completely separated from V and W. It just lives somewhere else. and f is just defined on v and w. So the linearity with respect of multiplication by scalar has this form: f applied to lambda times v is the same as multiplying on the left by lambda the image of v by f. And again, in the left hand side we have a multiplication by scalar using the structure of v, and on the right hand side the multiplication of lambda is using the structure of w, because f of v lies here in w. Linear applications are also called homomorphisms, as I have anticipated at the beginning of the lecture. Now let's consider a few properties of homomorphisms. If f is one of them, then the first property states that when you apply the homomorphisms to the identity element in the domain, we will get the identity element in the codomain. This follows from the property B, which is linearity with respect of multiplication by scalars, because if we apply f to the identity element of V, we can write the identity element of V as 0 times any element of the domain. By linearity, this is the same as 0 times the image of V, but 0 times any vector is always going to be the identity element of the vector space, which in this case is 0 of W. Property 2, f applied to the opposite of V is the opposite of the image, negative f of V. Well, this because of the same argument as in the part 1, in the property 1, and noticing that the opposite of V can be written as V multiplied on the left by a scalar, namely the scalar negative 1 in the field we are considering. Property 3 states that homomorphisms send vector spaces, subvector spaces to subvector spaces. If U is a vector space of V, then its image in W is going to be a subvector space of W. Moreover, if we fix a set of generators of U, namely Ui, then their images form a set of generators for the image of U through F. And the fourth property is somehow the dual of the third property. Instead of starting from a subvector space of the domain, we start from a subvector space of the codomain, and we consider its inverse image. F minus 1 of H is going to be a subvector space of V. However, the second part of the property 3 does not hold in this case, because if Hj is a set of generators of H, it is not always true that the pre-image of these generators, f minus 1 of Hj, are generators of the pre-image of H. Remark, property 3 implies that homomorphisms cannot increase dimension of vector spaces. So if you consider a vector space V and W, and you consider the subvector space in V, U, to be V itself, the second part of the property 3 simply implies that if we fix, for example, a basis of V, which is in particular a set of generators, its image has to be a set of generators for the image of U. So, in particular, suppose that there exists a surjective map from V to W, where W has a strictly higher dimension than V. Well, if it is surjective, that means that the image of V is all W, is all the codomain. And if the image has a strictly greater dimension than the domain, then this property cannot hold, because suppose that the domain has dimension n, and the codomain has dimension k, where k is strictly greater than n, if we take the image of n linear independent vectors in the domain, what we get is again n vectors in the codomain, and n vectors cannot be generators for a vector space whose dimension is strictly greater than n. Property 3 therefore implies that there cannot be a linear bijective map between these two vector spaces if n is different from m. To end the lecture, we give two notations. Well, the first notation I already used it a few minutes ago. Let's f be any set theoretic application and z a subset of w. Then the pre-image of z, so z lives here, the pre-image in of z by f, so we are talking about a subset of v, is defined to be the set of all the x's in v, which whose image is contained in z, whose image through f is contained in z, and this is a subset of v, and we call this pre-image of z by f. We just used this notation and this word a few minutes ago. Another fundamental wording is the following. Again, f is a linear map this time, so pre-image can be defined for any set theoretical map. Whereas the following one must assume that f is linear and pick y to be an element in w. Then, okay, the first statement is that the pre-image of an element in the codomain, assuming that is in the image of f, of course, otherwise the pre-image is the empty set. So if y is in the image of f, its pre-image in v is never a subvector space of v unless y is the zero vector of w. And this subvector space is called the kernel of f, and it's this is a fundamental notation and concept of linear functions between vector spaces and between any other object with algebraic structure.